Hello students, so today's question says, figure shows a man of mass 60 kg standing on a light weighing machine kept in a box of mass 30 kg. The box is hanging from a pulley fixed to the ceiling through a light rope, the other end of which is held by the man himself. If the man manages to keep the box at rest, what is the weight shown by the machine? Also, what force should be exerted on the rope to get his correct weight on the machine? This is the figure given, the first figure on the left. See that there is this man who's standing inside a box on a weighing machine, and he is holding this string, this rope, which is going over a pulley and is connected on the other side with the box itself. So see that man, as he pushes this string, the rope down, the rope will create the same force on the man in the upward direction. Yes. Apart from that, as the man is standing on the weighing balance, he will experience a force from the weighing balance also, and then there will be his own weight. So since we are supposed to find out the value of force that the man exerts on the string or the rope, it is essentially the tension force that will be created in the rope that we are supposed to find out, right? Because whatever force the man exerts on the rope becomes the tension in the rope. The rope is given to be light. So it's a simple question in the sense that you just have to get the free body diagrams of the two bodies here correctly. Once you get that, all you need to do is balance the forces and get your answers. So here on the right side, I have drawn the two FBDs, the free body diagrams, for the man here and for the box here, where you have to be a little careful while taking the directions and the values. See that for the man, there are three forces acting. One is his weight. The second one is the normal reaction that acts on it from the surface of the weighing balance. And the third is the force of tension. Mind you, it is the same force that the man is exerting on the rope, and then by the Newton's third law, the rope will exert the same force on the man in the opposite direction, which will be upward because the man is pulling the rope down. So this is what we have for the free body diagram of man. The second figure is for the box, where if you look carefully, the weight of the box is small mg. The tension that is created in the rope is acting on the box where the string, the rope is connected with the box, which is here at the top point. So T is acting on the box in the upward direction, and since the weighing machine is kept on the box, within the box, we can take it as a part of the box itself, so that the man, as he experiences a normal reaction from the weighing machine, the man will also exert the same force N on the weighing machine in the downward direction as a reaction to that. Yes, and this force N essentially will then act on the box itself. You can take this force as a force acting on the box through the weighing balance, of course. So these are the three forces acting on the box, and according to the condition given in the question, we are supposed to find out the value of T for which these two will remain at rest. So for rest, we understand that we just need to balance the forces acting on both the bodies. So when we use those equations for the man, this will come out to be the equation for net force on the man becoming 0. Net upward force N plus T is equal to the net downward force capital Mg. And for the box, the net upward force T is equal to the net downward force N plus small mg. You can easily solve this equation to get the value of N here. Maybe you can subtract the second equation from the first, so that T cancels out, and that will give you this equation, which you can further solve to get the value of N. I have substituted the values of capital M and small m given in the question to get this value for normal reaction exerted by the weighing balance. And understand that the weighing balance, when it shows you a certain reading, it is according to the force that it creates, normal reaction that it creates on the body which is kept over it. So if the weighing balance is reading a normal reaction of 15 g, the corresponding weight of the man that it will show in the scale will be 15 kg, right? So this is the first part of the question. Now the second part of the question is, we have to get that value of T, that value of force that the man must exert on the rope, so that his weight on the weighing balance becomes his correct weight. so that the weighing machine measures his correct weight, which basically means that the normal reaction that the weighing machine exerts on the man should now be equal to the weight of the man himself. So with that we come to the second part. So we say that to get the correct weight on the machine, the normal reaction exerted by the machine on the man should be equal to the weight of the man. And once again, when we draw the free body diagrams here, see that we have got the same three forces on the man as well as on the box, with one major difference now. And the difference is the fact that this time the system will not be at rest, it will not be in equilibrium. For equilibrium, because we have already got a condition which is now not being obeyed, right? Now the n value is different from what we have got above. So since n is not the same, we understand that the net force on the system, both the bodies, will not be 0 and the system will accelerate. So if we assume that, let's say, the system accelerates with an upward acceleration a, how do we know that the acceleration will be upward only? If you just look at the man's free body diagram, you understand that n and mg now are already balancing because of this condition. So that the only force that remains on the man is now the force of tension, the force in the rope. And this force is certainly in the upward direction on the man. And so the net force on the man is upward. So there is no other way the man can move. He can move only in the upward direction. Since the man moves in the upward direction and he is standing within this box, always in contact with the floor of the box, we understand that the box must also move with the same acceleration in the same direction. So we assume that, let's say, both the man as well as the box have a common acceleration a in the upward direction. Now we will formulate equations for both. So for the man, see that the equation for Newton's second law, net force is equal to mass into acceleration, will now be just T is equal to capital M into A. That's the only net force, T, acting on the man. Whereas for the box, we have three forces still, T in the upward direction, small mg in the downward direction, and n also in the downward direction. And the net upward force is equal to ma, gives you this equation this time. Net upward force is upward force minus downward force, that should be equal to mass into acceleration, where you now know that the value of n is equal to capital Mg, so you can substitute this value here. And now all you need to do is solve the two equations 1 and 2 to get your value for T. T is what they have asked for. T is the tension in the rope, is nothing but the force that the man exerts on the rope, right? So using equations 1 and 2, I have done this calculation here for you. You can just check it for details. You can easily use the equation 1 and substitute the value of, let's say, A from the equation 1 into equation 2 to get a relationship for T in terms of all the known values. And when you solve it, you get the value of T as 1800 newtons, which is the final answer for the second case. Thank you.